What if the universe wasn't what it seemed? What if the laws of physics, those firm rules we're taught in school, were full of cracks, riddles, and impossible loops? Tonight, you're not here to solve equations or memorize formulas. You're here to drift into a strange and silent descent through the most mind-twisting paradoxes modern physics dares to whisper about. These are the kinds of ideas that keep physicists awake at night and make reality itself feel like a fragile illusion. From particles that exist and don't exist at the same time, to the idea that time itself might move backward in hidden corners of the cosmos. Every section of this journey will take you one step further from what you thought was solid ground. We'll unravel light that carries darkness, gravity that repels, matter that erases space, and loops that never had a beginning. So, close your eyes and prepare to fall asleep to the bending, breaking, and rebuilding of the universe itself. Imagine you are watching a hummingbird in flight. Its wings beat so fast they blur into invisibility. But then, something impossible happens. The blur stops. The wings freeze mid-flap. The hummingbird hovers perfectly still, its body suspended in space, its wings no longer moving, yet somehow it remains afloat. Time hasn't stopped. The world around you continues. Leaves rustle, clouds shift, your heart beats, but the bird, its motion, is completely frozen. Welcome to the paradox of frozen motion, where movement seems to occur without actual change, and time appears to flow without anything progressing through it. This idea finds its roots in Zeno's ancient paradoxes, especially the arrow paradox. Zeno argued that for an arrow to fly, it must first occupy a position in space at any given instant. But at each of those instants, it's motionless, just sitting there, suspended. If every single moment is frozen, how can anything ever move? Put simply, if the present is always a snapshot, how can those snapshots add up to movement? Classical physics dismissed this as a trick of language, something smoothed over by calculus. But then quantum mechanics showed up, and suddenly, the freezing wasn't just philosophical. In quantum theory, particles don't move in the smooth arcs we imagined. Instead, they exist as probability clouds. Electrons don't travel like tiny billiard balls. They jump. Between states, between orbits, between energy levels. They teleport. They vanish and reappear in a new place. It's not motion in the traditional sense. There's no path. There's only a before and after. No in between. This strange behavior gets even more unsettling when we examine it through the lens of the quantum Zeno effect, a real tested phenomenon where simply observing a particle freezes its motion. The more frequently you look, the less it changes. Like catching the hummingbird mid-flap and keeping it there by sheer act of attention. Continuous measurement doesn't reveal movement, it kills it. So now, we're left with a haunting possibility. That motion, as we experience it, might be an illusion born from our limited perception of time. That objects don't actually move from one point to another, but rather appear at different locations based on shifting probabilities and observer interactions. Let's take it further. In certain theories of time, like Julian Barber's timeless physics, reality is made up of discrete nows. Each now is a complete universe in itself, a frozen frame. There's no actual flow of time. What we call motion is simply our consciousness sliding across these frozen frames, one after another, like a projector moving frame by frame through still images, generating the illusion of a movie. But in this view, every moment is eternally still. The universe never moves, only we do, through it. So maybe, just maybe, we are that hummingbird, frozen in one frame, in one now, hovering in stillness, while some deeper layer of existence plays us forward like a silent slideshow. And here's the twist that completes the loop. If all reality is made of frozen moments, then motion isn't a physical fact. It's a trick of memory, a ghost of continuity we impose on static worlds. Your breath, your heartbeat, the shifting weight of your body beneath the covers. What if none of these are truly moving? What if they are simply stillness stacked upon stillness, frames in a gallery mistaken for flow? In frozen motion, the laws of physics gently whisper that your sense of movement may be nothing more than a stitched illusion, and that behind the endless dance of time and space, everything might already be still. What if gravity didn't pull you down, but pushed you up? What if everything we thought we knew about falling, mass, and attraction was flipped inside out, not by fantasy, but by the hidden logic of the universe? The paradox of inverted gravity begins by asking one simple question. What if gravity isn't an attractive force at all, but a repulsive one we've misunderstood? To understand this, we need to challenge the comfortable notion that gravity is just mass pulling on mass. Newton described it that way, and for centuries, it worked. Objects fell, planets orbited, tides rose and fell. But Einstein changed that narrative with his theory of general relativity. Gravity, he said, isn't a force. It's the warping of space-time itself. Objects aren't being pulled, they're falling into dents in the cosmic fabric. But what happens when that fabric curves the other way? Imagine a universe not ruled by gravity that draws matter inward, but by a kind of anti-gravity, where the presence of mass creates a hill instead of a dent. Instead of attracting things, it repels them. Instead of drawing planets together, it sends them drifting apart. Strange? Maybe. But some physicists think this already happens, just on a larger, more hidden scale. This is where dark energy enters the picture, the mysterious force accelerating the expansion of the universe. Nobody knows exactly what it is, but it behaves like inverted gravity. Rather than pulling galaxies together, it drives them apart faster and faster. Something, somewhere, is pushing everything away. Gravity as we know it loses its grip at cosmic scales, and something else, something inverted, takes over. Now take that concept and apply it not to the universe, but to you. What if, in some hidden region of space, or even right beneath your feet, the rules reversed? What if, under the right conditions, gravity could become repulsive? Physicists have proposed this in the form of negative mass, a hypothetical kind of matter that, when pushed, moves toward the force instead of away from it. If such matter exists, it wouldn't fall, it would rise, not float, accelerate upward, endlessly. And now, here's where the paradox deepens. If negative mass were to interact with regular mass, the results would be catastrophic and beautiful. The two would chase each other forever. Regular mass pulling, negative mass repelling, locked in an endless loop of acceleration. This system would break our current understanding of inertia, motion, and energy conservation. It would rewrite physics from the inside out. The strangest part? Our equations don't forbid it. They allow it. But our reality doesn't. Or does it? Some speculative theories suggest that dark energy might be the large-scale effect of this repulsive gravity, that the fabric of space is subtly riddled with pockets of inverted gravity, hiding in plain sight, shaping the cosmos with invisible hands. It's not science fiction, It's just unconfirmed science, a possibility waiting for proof. And here's the philosophical twist. What if gravity was never a force at all, but simply a rule our minds created to make sense of a deeper truth? What if the real reality doesn't distinguish between pull and push, only between presence and absence of curvature in space-time? Imagine waking up tomorrow in a world where down was no longer down, where you stepped out of bed and floated upward toward the ceiling, your body pulled not by Earth, but by some ancient reversal you could never understand. Would you know what changed? Or would you, like everyone else, simply adapt and forget that gravity had ever pulled in the first place? Inverted gravity invites us to fall, not downward, but inward, into the terrifying idea that even the most fundamental force we trust could turn against us, or never have been what we thought at all. The universe began with a bang, but no sound. That's the first crack in the illusion. The Big Bang, often imagined as a colossal explosion, wasn't loud. It wasn't fiery. It wasn't even an explosion in the way we understand explosions. It was the birth of space, time, matter, and energy itself, emerging not into a pre-existing void, but creating the very stage upon which everything now exists. And yet, if this was the loudest moment in cosmic history, why was it silent? Welcome to the paradox of the silent bang, the moment that shook the entire universe into being, yet made no sound at all. To make sound, you need air, or gas, or particles that can vibrate, carrying pressure waves to a listener. But in the beginning, there was none of that. Just an unimaginable density and heat packed into a point that had no size, no ears to hear it, no medium to carry sound, and perhaps no moment in which it could be heard. So why do we imagine it as an explosion? Because our minds are trapped inside time, inside causality. We can't help but see beginnings as booms. A firecracker, a collision, a scream in the void. But the truth is stranger. The Big Bang wasn't an event inside space. It was an event that created space. And that means asking what it sounded like is like asking what lies north of the North Pole. The question collapses in on itself. Here's where the paradox deepens. The Big Bang wasn't silent because it lacked force. It was silent because it was everything. There was no outside from which to hear it, no frame of reference to compare it to. Imagine a painting that paints itself, a book that writes its first word without ink, pen, or page. The birth of the universe was like that. An act without a setting, a detonation without noise, a bang that never echoed. And yet, we can still hear it, faintly, indirectly. The cosmic, microwave background, a soft hum of ancient radiation, still echoes through space. Not in sound, but in energy. It's a ghost of that silent beginning. A whisper of heat stretched thin across billions of years. Every time we point a radio telescope into the sky, we're hearing the aftershock of a bang that made no sound. But here's the strangest twist. The Big Bang may have never happened at all, not in the way we think. Some physicists propose that the singularity, the infinite point of density and energy, never existed. Instead, time itself may be cyclical. The universe expands, contracts, and bounces back again. The Big Bang, in this view, was just one beat in an eternal rhythm. Not a beginning, but a breath, a pulse, and what we call the start of everything might just be a ripple in a much larger silent ocean we'll never fully see. Even more unsettling. Certain models of quantum cosmology suggest the universe may have emerged from a state of timeless quantum fluctuation. No cause, no before, just a spontaneous blip from nothing into something. No sound, because there was no time for sound to unfold in, only sudden presence. So the paradox remains. The silent bang was the loudest moment in existence, and no one heard it. Not because it was quiet, but because quiet and loud didn't exist yet. The very act of hearing was still billions of years away, waiting for stars, planets, and ears to evolve. And yet here you are, breathing, thinking, listening, in a universe that was once so silent it made no sound at all. But somehow, that silence gave birth to every heartbeat, every whisper, every crashing wave. The bang never needed a voice. It had you. Imagine you're standing alone in a room. You flip a coin, heads or tails. It doesn't matter, right? You see the outcome, you accept it, and life moves on. But in the quantum world, that simple act fractures the universe. Because somewhere else, unseen and unreachable, another you saw the opposite side of that coin. Welcome to the paradox of the quantum twin, a strange, unsettling idea that every decision, observation, or event may split reality into countless overlapping versions, each one containing a slightly different you. At the core of this paradox lies the phenomenon of quantum superposition, the idea that a particle can exist in multiple states at once. An electron can be both here and there. A photon can spin clockwise and counterclockwise. It's only when you observe it, when you measure it, that it chooses, or appears to. This is what the famous Schrödinger's cat experiment was meant to highlight. Until observed, the cat in the box is both alive and dead. But why does observation collapse the possibilities? Enter the many worlds interpretation of quantum mechanics. It doesn't say the other outcomes disappear. It says they all happen, just not in this version of reality. Every time a quantum event occurs, the universe branches. One universe where the cat lives, another where it dies. One where you make the call, another where you hesitate. A forked path into infinity. And that's where your twin comes in. Every time you make a choice, a copy of you, your quantum twin, makes the other one. You go left, they go right. You stay, they leave. They are you in every way except for one tiny divergence, and they too believe they are the original. But here's the twist. You can never meet them, never cross over, never wave hello through the mirror of branching universes. The very structure of quantum mechanics keeps these realities from bleeding into each other, and yet, their existence may be necessary to explain the probabilities we observe. You see only one outcome, but the math demands all possibilities remain alive. Still, the idea is more than just a mathematical trick. The double-slit experiment, where particles fired one at a time create interference patterns as if they traveled through both slits simultaneously, seems to hint at something eerie. The particle behaves as though it knows all possible paths, even when you're not watching. And when you do watch, it collapses to one. But which one? According to the many worlds view, it doesn't collapse. You just become one version out of many, and your twin sees the other. But this leads to a horrifying question. If every version of you exists, if every outcome plays out, what does that say about free will? Are you choosing your path, or are you simply traveling down one of infinite tracks with copies of you riding the rest? And what happens to the versions of you who suffer, who fail, who die? If they're just as real as you, does your success matter more? Or are you simply the one who got lucky? Now take a moment, lying there in bed, and imagine all the other yous blinking into reality right now. One is reaching for their phone, another is asleep already. One is laughing, one is crying. Some are living lives you can't begin to imagine, some never existed at all, and some might be imagining you as their twin. This isn't science fiction, it's a plausible interpretation of one of the most successful scientific theories ever devised. And yet, it leaves us with a quiet unease. Because if every you is real, then who are you? The quantum twin is the ghost of your other life, always close, never seen. A reminder that you are both unique and endlessly multiplied. You are one of infinite reflections, and somewhere, out there in the branching dark, your twin is wondering the same thing. Close your eyes and imagine a perfect mirror. Not a dusty glass pane, but a cosmic mirror. One that reflects not just light, but the fundamental structure of reality. In this mirror, every force has its equal. Every particle has its twin. Every action has its perfect opposite. This is the universe as it should be, balanced, symmetrical, whole. But now, imagine watching that mirror crack. The paradox of shattered symmetry lies at the very heart of physics. We used to believe that the universe was symmetrical, that it treated left and right, forward and backward, matter and antimatter the same. But nature, it turns out, plays favorites, and the universe we live in is fundamentally broken in subtle, terrifying ways. One of the first signs of this came with the discovery of CP violation. CP stands for charge and parity. Two properties that should, in theory, keep the universe fair and balanced. If you flip the charges of particles and reflect their spatial orientation, their behavior should remain unchanged. That's what symmetry demands. But in 1964, physicists watched particles called kaons decay in ways that violated this sacred balance. The mirror didn't reflect the way it was supposed to, and that raised a terrifying question. Why does the universe break its own rules? The consequences are profound. If symmetry were preserved, matter and antimatter would have annihilated each other after the Big Bang. The universe would be empty, pure radiation, no stars, no planets, no you. But for some reason, matter won. A tiny imbalance, one extra particle of matter for every billion of antimatter survived. Enough to build galaxies, enough to build you. But why did symmetry shatter at all? No one knows. It's as if the universe rolled dice at the moment of creation and cheated. And once that first crack appeared, the rest followed. Today, we see asymmetry everywhere. The weak nuclear force violates mirror symmetry completely. Time flows forward, not backward. Left-handed particles behave differently than right-handed ones. Somewhere in the early moments of time, the universe chose a direction and never looked back. And here's the deeper paradox. The laws of physics themselves remain symmetrical, at least on paper. Our equations are elegant, balanced, beautiful, but the universe they describe is not. The math allows a perfectly symmetrical world, but reality doesn't reflect it. The mirror is shattered, and we don't know who or what threw the stone. This imbalance isn't just abstract. It's built into your body. Your molecules twist in left-handed spirals. Your proteins fold in asymmetrical ways. Life itself depends on this broken symmetry. If the mirror hadn't cracked just so, biology might never have emerged. Some physicists believe symmetry once existed in full, hidden form, perhaps during the earliest stages of the Big Bang, a phase where all forces were unified and the universe was smooth and perfect. But as the cosmos cooled, it underwent spontaneous symmetry breaking, like a ball rolling off a hill and choosing a random valley to settle in. One choice among many, but irreversible. From that one decision came the laws of physics, the flow of time, the structure of matter. Others suggest that symmetry wasn't broken by accident, but by necessity. That complexity, structure, and consciousness require imbalance. That perfection is too still, too dead, to produce life. That only by shattering the mirror could the universe become strange enough to think about itself. So tonight, as you drift into sleep, remember this. The world around you exists not because it's balanced, but because it isn't. You are the product of a broken rule, a crack in the glass, a moment when the universe bent its own laws and never went back. Shattered symmetry is the paradox of beauty found in imperfection, of laws betrayed by their own outcomes, and of existence arising, not from harmony but from fracture. Time moves forward. That's the one rule everyone agrees on. We're born, we age, we die. Clocks tick, suns rise and fall. Milk spills, but never unspills. You never see smoke flowing back into a cigarette, or a shattered glass pulling itself together. The arrow of time always points one way, forward. But what if that arrow isn't absolute? What if now isn't just sliding into the future, but simultaneously leaking backward? This is the paradox of backwards now, the haunting idea that the present might influence not only what comes next, but what came before. At first it sounds impossible. Cause leads to effect. That's how everything works. You press a button and the elevator comes. You sneeze and the sound follows. But modern physics, especially quantum mechanics, quietly suggests that causality might not be as firm as we think. Let's begin with a thought experiment called the delayed choice quantum eraser. In this bizarre setup, a particle is sent through a pair of slits and behaves like a wave, interfering with itself, as if it went through both slits at once. But if you later, after the fact, choose to observe which slit it passed through, the interference pattern disappears. The particle seems to know whether it will be observed in the future, and it changes its past behavior accordingly. Let that sink in. A decision you make in the present appears to rewrite the particle's history. The future reshapes the past. This isn't science fiction. It's been demonstrated in real experiments. Though controversial and hotly debated, it leaves a door open to one chilling conclusion: that the boundary between past, present, and future is blurrier than we've been told. Physicists call this retrocausality, the idea that effects can travel backward in time. In some interpretations of quantum theory, like the transactional interpretation, particles send signals both forward and backward in time simultaneously. Every quantum interaction becomes a handshake between the past and future, meeting in the now. But if the present influences the past, what does that make now? Maybe now isn't a moment at all, but a collision. A meeting point between timelines bleeding into each other. A ripple that flows in both directions. You feel time moving forward because your memory is built that way. But the fabric of reality might be echoing in reverse just as strongly. Even in thermodynamics, the rules get shaky. The second law tells us entropy, disorder, increases over time. That's why you remember the past and not the future. But the laws of physics themselves are time symmetric. They work the same forward and backward. There's nothing stopping time from reversing, except our perception of it. So what if now is not the midpoint between what was and what will be, but the seam where what could have been gets overwritten by what must be? What if each passing moment isn't just building the future, but rewriting the past over and over, retroactively locking it in? And here's the existential twist. How would you even know? Your memories feel solid, but they're electrical shadows in a brain. If reality adjusted a microsecond ago, if the timeline subtly rewrote itself, you'd have no reference point. You would remember the adjusted past as if it always happened that way, and you'd be none the wiser. In Backwards Now, the present becomes a mirror, casting light not only forward into time, but backward into the roots of what brought it here. Your choices today may ripple into the past, and the past you remember may be nothing more than a reflection of a future already decided. So as you lie here, caught in the stillness between seconds, consider this. Maybe now isn't just moving forward. Maybe it's breathing, expanding in both directions. And somewhere deep beneath your conscious awareness, the future might already be remembering you. You felt it before. That unspoken force nudging the universe along. You drop an object and it falls. You lean forward and the floor resists. You feel weight, pressure, motion. It's always there, unseen, unfelt directly, yet undeniably real. We call it force. We call it interaction. But what if it's all an illusion? Welcome to the paradox of the invisible push. The idea that what we experience as force, pressure, or even contact might not exist at all. That the universe is not pushed into action, but operates entirely through empty space, tensionless fields, and the illusion of touch. Let's begin with something simple. Your hand pressing against a table. It feels solid. You feel resistance, but zoom in and everything changes. On the atomic level, your hand never actually touches the table. The electrons in your skin repel the electrons in the wood. The sensation of contact is nothing more than electromagnetic repulsion. No two atoms ever meet. They're kept apart by invisible fields, and your brain interprets that as touch. Now, expand this concept. What about gravity? For centuries, we imagined it as a force pulling objects together. But Einstein's theory of general relativity shattered that illusion. Gravity isn't a force at all. It's the curvature of space-time. Objects fall not because they're pulled, but because space itself bends and funnels their motion. They're not being pushed or pulled. They're following straight lines in a curved world. So here's the paradox. What if every force you've ever felt is fake? Even the strong nuclear force, the one that holds protons and neutrons together in the atom, is mediated by exchange particles. The force isn't a push, it's a message, a quantum transaction between fields. The same is true for the electromagnetic and weak nuclear forces. They aren't shoves, they're agreements, temporary exchanges, virtual particles whispering across the void, deciding the fate of matter. And in quantum field theory, it gets even stranger. All particles are just excitations, vibrations, in invisible fields spread across the universe. A photon isn't a thing flying through space. It's a ripple in the electromagnetic field. An electron is a ripple in the electron field. These ripples don't push or pull. They interfere, they collide, they cancel or amplify each other. No hands, no hooks, no strings. So why do we feel the push? Because our brains evolved to survive, not to perceive quantum truths. Your body interprets molecular repulsion as pressure. Your neurons convert atomic standoffs into sensation. It's a convenience, a simplification, like a video game's physics engine, real enough to play, false enough to hide the underlying code. But what if something deeper is missing? In some speculative theories, like the entropic gravity hypothesis, gravity isn't even a fundamental force. It's an emergent phenomenon, like temperature. When you feel heat, you're not feeling a heat force. You're experiencing countless, microstates blending into a single sensation. Gravity might be the same, a macroscopic side effect of microscopic entropy. Not a pull, not a push, just imbalance. Systems trying to settle. If that's true, then the very foundation of our experience, force, isn't fundamental. It's a symptom. So here's the mental trap. The invisible push may not be a push at all. The universe may be a ballet of information swaps, of probability waves nudging each other without ever touching. You're not walking on the ground. You're floating on layers of unspoken agreements between fields. The table doesn't hold your hand up. It simply refuses to collapse its own electrons into yours. And yet, somehow, the illusion is perfect. The paradox of the invisible push is that reality feels solid, reactive, and responsive. Yet underneath, there are no hands, no pressure, no real force. Only distance, only repulsion, only interaction across emptiness. So, the next time you feel the world resist you, remember, it's not resistance. It's misunderstanding. The universe doesn't push. It pretends. There's a box in front of you. Inside it, sealed away, is a cat. Alongside the cat is a radioactive atom, a vial of poison, and a Geiger counter. If the atom decays, the counter detects it, shatters the vial, and the cat dies. If the atom does not decay, the cat lives. The twist? The decay is a quantum event, uncertain, unpredictable, and until you open the box, quantum theory says something chilling. The cat is both dead and alive. Welcome to the paradox of dead alive, perhaps the most iconic and disturbing illustration of quantum weirdness. This thought experiment, proposed by Erwin Schrödinger in 1935, wasn't meant to explain quantum theory. It was meant to mock it, to highlight the absurd implications of applying quantum rules to the macroscopic world. But nearly a century later, physicists still take it seriously. At the heart of this paradox lies superposition, the idea that a quantum system can exist in multiple possible states at once. An electron can spin up and down. A photon can pass through both slits. A particle can be here and there. But when we observe the system, the superposition collapses into a single outcome. Until then, all possibilities coexist. So, what does that mean for the cat? If we accept the rules of quantum mechanics as universal, then before we look inside the box, the radioactive atom is both decayed and not decayed, which means the vial is both broken and unbroken, which means the cat is both dead and alive, not metaphorically, not hypothetically, literally both states at once, superimposed, entangled, real. The act of observation collapses the wave function. But why? What makes you, the observer, so special? Why should your awareness trigger reality to choose? This is where things unravel. Some interpretations say it's not your consciousness, but the interaction with the measuring device that collapses, the state. Others say wave function collapse never really happens at all, that every possible outcome branches into its own universe, just like in the many worlds interpretation. In that view, when you open the box, you split. One version of you sees the dead cat. Another sees it alive. Both are equally real. In other words, the paradox isn't in the cat, it's in you. Even more unsettling, scientists have now created Schrödinger-like states in real lab experiments. Superpositions of molecules, of vibrations, of light. We've coaxed tiny systems to exist in multiple states, pushed the boundary of quantum into the visible world. And though no one has yet done this with a cat, the theoretical possibility remains. There is no clear line between the quantum and the classical world. The cat is a symbol, but the physics is real. So what does this mean for life and death? What if death, like position or spin, is just another probabilistic state? What if consciousness exists in a fragile superposition between presence and absence, until something, an accident, a heartbeat, a breath, collapses it? The dead-alive paradox forces us to reconsider the finality we assign to endings. The cat is not just a pet in a box, it's a mirror, a metaphor for our own uncertainty, for every moment we exist without knowing if the next will come, for every heartbeat that could, in theory, be the last, or not. And maybe this isn't just a quirk of atoms. Maybe existence itself is quantum. Maybe we are all Schrödinger's cats, walking wave functions, always halfway between what is and what might be, alive in some futures, dead in others, flickering, in and out with every choice, every chance. As you lie there, breathing, consider that strange possibility. You may not be as definite as you think. You are alive, but perhaps somewhere deeper in the folds of the universe, another version of you already isn't, or maybe somehow you are both. What is light? You might say it's what lets you see, that it travels from the sun or a bulb, bounces off objects, and enters your eyes, that it moves incredibly fast, 186,000 miles per second, that it's both wave and particle. All of these are true, and yet, none of them capture the deepest mystery. Light doesn't experience time. This is the paradox of lightless light, a concept that challenges not just your understanding of light, but of time, motion, and the very structure of reality. According to Einstein's special relativity, the faster you move through space, the slower you move through time. At the speed of light, time stops entirely. A photon, the quantum particle of light, travels through the universe without aging. From its own perspective, it's emitted and absorbed instantly. The journey from star to eye, from galaxy to telescope, happens in zero time. For a photon, there is no distance, no in-between, no before and after, just a flicker of presence that exists without a journey. So here's the first layer of the paradox. We experience light as something that travels, yet to light itself, travel doesn't exist. Now, imagine this. You're looking at a star 100 light years away. The photons hitting your eyes left that star a century ago. You see it as it once was, not as it is. But the photon doesn't remember those years. It wasn't slowly making its way across the void. It simply appeared, instantly, from its own frame of reference, at its destination. It never experienced the in-between. How can something move across time and space, yet experience neither? It gets weirder. Light is also the universal speed limit. Nothing with mass can reach it. As you approach light speed, your mass becomes infinite, and time slows to a crawl. But photons, they exist right on that edge, massless, timeless, structureless. They are not just moving through reality. They may be defining its structure from outside time itself. And yet, despite this ghost-like nature, light governs everything. It mediates the electromagnetic force. It brings warmth, vision, color. It powers photosynthesis, drives weather, and sculpts the cosmos. Our entire biological existence depends on light, a force that, from its own perspective, never truly travels. That's the next layer of the paradox, something that never ages, never travels, and never occupies time, is the very thing that shapes all of time-bound life. And here's where the paradox deepens into the philosophical. If photons don't experience time, then can we even say they move at all? If their beginning and end points are the only things that exist for them, what happens in between? Is there a gap, a void? Or are we inventing the illusion of a journey where none exists? This touches on a broader truth. The universe may be built on shadows we can never fully see. Light brings visibility, but its own experience is invisible. It is the carrier of information, but it has no information about itself. It reveals the world to us while remaining a mystery unto itself. And it doesn't end there. In quantum mechanics, light can interfere with itself, split, recombine, vanish, and reappear. Photons can become entangled, travel as waves, and collapse into points. Sometimes, light doesn't even need to be present for it to affect the outcome of an experiment. Its possibility alone changes reality. So we return to the paradox. Light is the most visible thing in the universe, yet it may be the most unknowable. You see by it. You live by it. But you will never truly touch it, never feel what it feels, never understand what it knows, because light, as it turns out, is not just something that moves, it is something that transcends. Lightless light is the paradox of movement without time, of presence without path, of the thing that shows everything while hiding its own truth, a ghost woven into every corner of the universe, a journey that never began, yet somehow ended in your eyes. Fire devours. It dances, consumes, radiates heat. It's wild, chaotic, always needing something to burn, always leaving something behind. Ash, smoke, carbon. It's the image of destruction tied to friction, to the resistance between materials that fuels the flame. But what if fire could exist without friction? Without combustion, without heat? Welcome to the paradox of the frictionless burn, a phenomenon that isn't a flame, but behaves like one. A burning that doesn't burn, a fire that leaves no ash. A paradox found not in forests or stoves, but in the deepest, coldest, strangest corners of physics. To understand this, step away from traditional fire and towards superconductors, materials that, when cooled near absolute zero, allow electricity to flow without resistance. No energy is lost, no heat is created. Imagine an electric current running through a loop forever, endlessly, without a battery, without degradation. That's a kind of frictionless energy, one that behaves like a self-contained burn with no cost. But what truly mirrors the paradox is the behavior of superfluids, liquids like helium, cooled to near zero temperatures, that lose all internal friction. They flow endlessly without slowing down. Spill a superfluid and it will climb up walls. Stir it and it will spin forever. It defies logic, as if it's immune to the very laws that govern matter. It's liquid, but also ghostly, possessing motion without decay, energy without waste. It's not alive, but it moves like something burning silently in time. Now combine this with the idea of quantum tunneling, where particles pass through barriers they shouldn't be able to cross. No force pushes them, no friction stops them. They just appear on the other side, as if the rules blinked for a moment. It's not motion. It's more like disappearance and reappearance, a spark with no flame. These phenomena, superconductivity, superfluidity, tunneling, aren't metaphors. They're real, and they challenge our understanding of what it means to expend energy, to move, to burn. Because in our world, movement and energy loss go hand in hand. Friction is the price we pay for motion. Heat is the tax for energy. But in the quantum world, that tax can vanish. Here's where the paradox ignites. If energy can move endlessly without loss, does that mean we can have eternal engines, infinite cycles, systems that never decay? Physicists say no. Eventually, entropy creeps in. But the very fact that we can create near-zero loss systems even for a short time suggests that nature, at its core, doesn't require friction. We do. We evolved in a hot, messy, resistive world. Our experience of heat, of fire, of effort is biased. It feels universal, but it's local. The cosmos, on the other hand, is cold, silent, and filled with places where energy flows like wind across ice. Fast, clean, eternal. So what is the frictionless burn? It's the illusion of fire without flame, the motion without resistance, the quiet energy that loops forever. And it asks a deeper question. Is destruction necessary for power? Must everything burn to be useful? Or have we just never learned to see energy that doesn't scream? There may be civilizations or machines built not on fire, but on flows, not on combustion, but on coherence, not on heat, but on harmony. And perhaps one day, we'll learn to tap into those rivers of frictionless energy and leave our burning behind. Until then, remember, the universe contains fires that don't burn and motion that doesn't slow. Somewhere, deep beneath the chaos of everyday heat and noise, something is spinning forever. Imagine looking into a mirror, not one that reflects your face, but one that reflects your actions. You raise your hand, and in the mirror, the reflection does the same. Simple, intuitive. But now imagine this. You raise your hand only because the reflection did it first. You didn't cause the mirror, you responded to it. This is the paradox of the causal mirror, a mind-bending loop where cause and effect blur, reversing roles, each depending on the other, like two dancers whose steps are locked in perfect symmetry, with no clear lead. In everyday life, causality feels solid. One thing happens, then another. Strike a match and it lights. Sneeze and someone blesses you. The arrow of cause and effect keeps time moving forward. But physics, especially quantum physics and relativity, doesn't always respect that simplicity. Let's begin with entanglement. When two quantum particles become entangled, they share a state. Measure one, and the other instantly reflects that result, no matter the distance between them. Einstein famously called this spooky action at a distance. But here's the catch. Which measurement comes first? If both particles are in motion and their clocks disagree, then the question of who caused what becomes meaningless. Both outcomes exist in a strange, mirrored dance of causality. Even worse, in some experimental setups, the choice of how to measure one particle appears to retroactively affect the earlier state of its twin. In other words, the future changes the past. The cause and the effect switch places, like a mirror that doesn't just reflect you, but instructs you. This isn't just philosophical musing. In Wheeler's delayed choice experiment, photons behave differently based on decisions made after they've passed through a slit. The photon seems to know in advance what the experimenter will choose and adapts accordingly. It's as if reality is waiting to be told what it should have been. So how can this be? How can the effect precede the cause? Some physicists propose time-symmetric theories where events are determined not just by initial conditions, but by final ones too. The universe doesn't unfold like a domino chain. It arranges itself like a completed puzzle, with both beginning and end shaping the middle. In this view, the future isn't just waiting to happen. It's already there, feeding influence backward into the past. The mirror doesn't just reflect, it pushes. The causal mirror also appears in closed time-like curves, hypothetical pathways through space-time that allow for time travel. If you send information back in time, and that information causes you to send it in the first place, who started the loop? There's no origin, just a self-contained reflection with no source. A mirror loop. And here's the deeper twist. What if this isn't rare? What if your reality is shaped by echoes from the future? Every time you make a decision, could it be influenced by something waiting at the end of time? Could the present be a compromise between memory and destiny? Between what you recall and what must eventually be? It sounds impossible, but physics doesn't forbid it. Our human minds crave linearity, but the universe may be non-linear, recursive, reflective. Time might not flow. It might stand still, eternally balanced between beginning and end, mirrored across the moment you call now. In the causal mirror, every action is both cause and effect. Every reflection you see might be the original. Every step forward might be guided by its echo from the future. So next time you feel yourself making a choice, turning left instead of right, speaking instead of staying silent, ask yourself, am I deciding, or am I reflecting something that's already been decided? What if emptiness isn't empty? When we think of a vacuum, we imagine absolute nothingness, a place without air, particles, energy, or matter, a pure void. But quantum physics tells a very different story. In fact, the more we study nothing, the more it seems to be everything. Beneath the silence of the void hums a storm of restless, invisible energy. This is the paradox of the wired vacuum, a reality where empty space isn't empty at all, but a seething, chaotic network of invisible potential, brimming with fluctuations, fields, and spontaneous creations. In quantum field theory, every point in space is alive with possibility. Even in a perfect vacuum, particles pop in and out of existence constantly. Virtual particles that flicker into being for fractions of a second before annihilating. They can't be directly observed, but their effects are very real. These ghost particles can shift atomic energy levels, generate tiny forces, and even affect the expansion of the universe itself. One famous example of this is the Casimir effect. Take two uncharged metal plates and place them extremely close together in a vacuum. You'd expect nothing to happen. There's no air between them, no obvious force. But they begin to pull toward each other, as if gripped by unseen hands. Why? Because the vacuum between them can't sustain the same quantum fluctuations as the space outside. The plates are essentially shielding each other from some of the vacuum's internal chaos. The result? A measurable pressure from nothing. This reveals a shocking truth. What we call empty space is actually filled with energy, not just metaphorically, physically. The vacuum is a wired network of interacting quantum fields, each one vibrating even when nothing is present. But the paradox deepens. This invisible structure of space may be responsible for one of the greatest mysteries in cosmology. Dark energy. The universe is expanding, and that expansion is accelerating. Something is pushing galaxies apart faster and faster, and we don't know what it is. But many physicists suspect that the vacuum itself, with its built-in energy, is to blame. This would mean the void isn't passive, it's active. It's not the backdrop of reality, it's the engine. Now here's where the paradox becomes unnerving. If vacuum energy is real, and it is, why don't we see more of it? Quantum theory predicts the energy of empty space should be enormous, enough to tear atoms apart and collapse the universe. But when we measure it, it's incredibly tiny. The difference between prediction and observation is the largest known mismatch in physics, over 120 orders of magnitude. That's a 1 followed by 120 zeros. This is known as the vacuum catastrophe, and it's not just a miscalculation, it's a mystery. Why is the vacuum so active, yet so quiet, so wired, yet so subtle? One possibility is that the vacuum is finely tuned, a delicate balance of energies, some positive, some negative, cancelling each other almost perfectly. Another is that we're only seeing a small part of a larger multiversal system, and in other regions, the vacuum behaves very differently. Perhaps in some realities, the void is so energetic that nothing can exist. In others, it's so dead that even time can't unfold. And here's the most unsettling idea. If the vacuum is full of hidden energy, then the true substance of the universe is nothing. Matter, galaxies, atoms, you, me, we're just brief disturbances in an otherwise empty sea of quantum noise. We think we live in a world of things, but really, we live in a world of fluctuations. The wired vacuum forces us to confront the ultimate illusion that the universe is made of stuff. It isn't. It's made of fields, of tension, of invisible connections that never go silent. So when you close your eyes tonight and imagine the emptiness between the stars, remember, that void is alive. It listens, it hums, it connects everything, even here, even now. Time, as we know it, is a river flowing forward. You wake, you live, you sleep. Events stack in sequence. Memories pile up behind you, and the future remains silent, unseen. That's how it feels. That's how we survive. But what if time doesn't flow at all? What if it echoes? This is the paradox of echoing time, the strange possibility that time might not be a straight line, but a resonance, a loop, a reverberation of patterns replaying themselves endlessly, like a melody forgotten by the mind, but remembered by the universe. Physics has long struggled with the nature of time. In classical mechanics, time is simply a parameter, an arrow, a constant drumbeat outside the system. But in Einstein's relativity, time is flexible. It bends, it stretches, it slows down in gravity, it speeds up in vacuum. Time is no longer absolute. It's stitched into space, curving with it, twisting with motion. But relativity doesn't tell us what time is, and neither does quantum mechanics. In fact, most of the equations that govern the microscopic world, like Schrödinger's equation, work perfectly in both directions. Run the math backward, and the universe still makes sense. There's no inherent preference for forward or backward. Time's arrow, it seems, is a human construct, one born from entropy, memory, and perception. So what happens if we strip all that away? What remains may not be time as we know it, but echoes, repeating patterns, recursive structures embedded in the fabric of the cosmos. Theoretical physicists have begun to explore models where the universe is cyclical. The Big Bang wasn't the beginning, but the end of a previous cycle. Expansion gives way to contraction, heat to cold, chaos to silence. Then it all begins again. Not a replay, but a resonance. Similar shapes returning like refrains in a cosmic song. This isn't a new idea. Ancient cultures often imagined time as circular. The Hindu concept of yugas, the Mayan calendars, the Ouroboros serpent devouring its own tail, all spoke of cycles, of time looping back on itself. But now, physics is catching up. One modern theory, conformal cyclic cosmology by Roger Penrose, suggests that each universe ends in such a smooth, stretched-out state that it's indistinguishable from the high-energy, low-entropy state that begins the next. In that framework, the end of time is also the beginning, a mirror where the final breath of one reality becomes the first gasp of another. And here's where the paradox takes shape. If the future loops into the past, then time is not linear but echoed. Events may not repeat exactly, but their structure does. Patterns resonate across cycles. Galaxies form in familiar spirals. Consciousness re-emerges. You may not return, but something like you might. Some fragment, some tone in the chorus. The implications are dizzying. What if déjà vu is a glitch of cosmic resonance? Your brain briefly syncing with an echo from a previous cycle? What if dreams are fragments not just of memory, but of time's deeper rhythm? What if everything you are is part of a chord, a vibration in the song of time, heard again and again, in different keys, through different lives? Even more disturbing, what if your fate isn't fixed but recurring? Not because it must happen, but because time favors certain notes. The universe is vast, but maybe it doesn't improvise. It composes, over and over. In echoing time, the present becomes both ripple and reflection, a shimmer from the past and a whisper of what's to come. It is not a moment, but a resonance, repeating across realities like footsteps in a canyon. So tonight, as you sink into silence, remember, the moment you are living may have been lived before, not exactly, not consciously, but rhythmically, echoed, like the last breath of one universe, reaching into the first breath of the next. Falling is something we all understand. You let go of a ball and it drops. Jump and you return to the ground. Gravity pulls, always down, always inward, always toward the densest mass nearby. It's one of the most familiar forces in the universe. But what if falling didn't mean down? What if gravity, the force that grounds us, could also become the force that lifts us away? This is the paradox of falling up, a reversal of our deepest intuition, where gravity doesn't pull you to the center, but pushes you toward the edge. It begins with a simple observation. Gravity, as described by Einstein, is not a force in the traditional sense. It's the curvature of space-time. Mass bends the fabric of reality, and objects move along the curves. They're not pulled, they're guided. You fall not because Earth reaches up and grabs you, but because space-time slopes downward, and you're simply sliding along the path. Now flip the slope. In regions of space dominated by dark energy, something strange happens. Galaxies don't cluster closer, they drift apart, accelerating away from each other. Instead of falling inward, space itself seems to be pushing everything outward. It's as if the universe is wrapped in a gravitational field that repels rather than attracts. Not falling down, but falling up into ever-expanding space. And it gets weirder. Theoretical physics allows for the existence of negative mass, a hypothetical form of matter that doesn't obey the normal rules. If you push negative mass, it accelerates toward the force instead of away. Even more bizarre, if a negative mass object encounters a positive mass, they would both accelerate together, one pushing, the other pulling, forever. A system that constantly increases in motion, violating every intuitive law of inertia and stability. In this strange framework, negative mass would naturally fall upward. It wouldn't settle into the center of gravity like regular matter. It would float, rise, repel. Gravity would act in reverse. And yet, we don't observe such matter in our universe, or do we? Some physicists speculate that dark energy, the mysterious force accelerating the cosmos, might be a manifestation of negative pressure or negative mass. If that's true, then much of the universe may already be falling up. Entire galaxies slipping away from each other, not pulled by gravity, but repelled by it. Now imagine standing on a planet made of negative mass. Drop an object, and it won't fall, it'll rise, jump, and you won't come down. You'll drift upward, away from the surface. The horizon curves inward, the ground repels your weight. Every motion contradicts your instincts. And here's where the paradox hits home. Falling is a relative experience. In Einstein's thought experiments, someone in a sealed elevator in deep space wouldn't know whether they were feeling gravity or accelerating upward. The effects are identical. Down is only down because your frame of reference tells you so. Flip the context, and down becomes up. Falling becomes rising. Gravity becomes anti-gravity. So what if, right now, in this moment, you're not being pulled toward Earth, but being pushed away from some deeper center you can't see? What if gravity isn't a force pulling you down, but a pressure pushing you up into the curved landscape of space-time? And what if falling is simply movement along the path of least resistance, whether that means collapsing inward or expanding outward? The paradox of falling up reminds us that our intuition, grounded in experience, may be entirely unfit for the true nature of the cosmos. In some corners of the universe, gravity lifts, mass repels, and the very concept of direction dissolves into geometry. So as you lie still, feeling the weight of your body, consider this. Your sensation of down may be a lie. You might not be sinking into gravity, but rising through it. Infinity is supposed to mean freedom, endless distance, endless time, endless possibilities. It's the ultimate expanse, the horizon that never ends. But what if infinity could trap you? What if the very concept of endlessness could imprison your thoughts, your logic, even your physics? This is the paradox of stuck infinity, a place where motion never ends, yet nothing changes, where time flows forever, but nothing is ever resolved. A paradox that doesn't unfold in space, but in loops, equations, and the mind itself. Let's begin with Zeno's paradox of the arrow. An arrow in flight, when observed at any single instant, is motionless, freeze time, and it's not moving. It just exists at one location. So if all time is made of instants, and at each instant the arrow is still, how does it ever move? The resolution, of course, lies in infinity. Infinite instants, infinitely, close together, can add up to motion. Calculus handles this elegantly with the concept of limits, but Zeno's paradox still haunts us because it shows how infinity, while logical, remains slippery. Every motion is an infinite series. Every second contains an infinite number of subdivisions. Yet we never reach the limit. We are always approaching, always stuck in the unfolding. Now take this to physics. In cosmology, we often speak of an infinite universe, stretching without end in every direction. But in general relativity, space can be both infinite and curved. You can have a universe that expands forever, but loops back on itself, like a higher dimensional sphere. You travel in one direction eternally, and eventually return to where you started. You move infinitely far, yet go nowhere, or take black holes. From the outside, a falling object seems to slow down as it approaches the event horizon, never quite crossing. To a distant observer, the object takes infinite time to fall. Yet from the falling object's perspective, it crosses the horizon in finite time. Two versions of reality, one where falling never ends, another where it ends swiftly. Both correct, both contradictory. Time becomes stuck, stretched into infinity from one viewpoint, but not the other. And then there's eternal inflation, the idea that our universe is just one bubble in a much larger inflating multiverse. In this model, new universes constantly bud off from inflating space forever. There is no end, no final snapshot of the cosmos. The process never completes. Time becomes an infinite canvas where no full picture is ever drawn. Infinity becomes the prison. But the most profound example of stuck infinity may come from mathematics itself. Some problems, like the halting problem in computer science, ask whether a given program will ever stop. Alan Turing proved that, in general, there's no way to know. Some processes may run forever. They are trapped in infinite loops, mechanical, thought patterns that never resolve. And perhaps you felt this too. Not with numbers, but in your mind. A question that has no answer. A fear that loops back on itself. A thought you can't escape. Repeating, echoing, stretching into mental infinity. So here's the twist. Infinity is not always freedom. Sometimes it's a cage. In stuck infinity, nothing is still, but nothing is different. It's motion without arrival, time without progress. A paradox where eternity is not a blessing, but a trap of endless unfolding. Whether in cosmic loops, endless expansion, black hole time dilation, or unsolvable logic, the infinite can become a snare. And yet, we depend on it. Without infinity, calculus fails, physics collapses, measurement breaks. We need infinity to explain, change, but it also makes finality impossible. So as you lie here tonight, drifting through your own thoughts, consider this. Maybe you're not moving through time at all. Maybe time is looping through you. Maybe your life, your breath, your mind are echoes in an infinite chamber, endlessly bouncing, never arriving. Mass is one of the most fundamental concepts in physics. It gives objects weight, inertia, and gravitational attraction. It grounds us, literally, binding planets into orbits and holding galaxies together. But what if mass could be negative? What if there existed a kind of matter that didn't fall down but pushed upward, that didn't resist force but rushed toward it? Welcome to the paradox of negative mass, an idea that turns the entire framework of physics inside out, where the rules we rely on suddenly behave in reverse. In classical Newtonian mechanics, force equals mass times acceleration, F, AMA. That equation seems straightforward. Apply a force and an object accelerates in the direction of that force. But if the mass is negative, then the acceleration is in the opposite direction. Push it forward, and it moves backward. Pull it toward you, and it runs away. This behavior defies every intuition we have. Imagine a ball made of negative mass. You kick it. Instead of flying away, it rushes back at you. You try to pull it closer, it escapes. It's not just disobedient, it's inverted. Everything it does is a mirror image of what you expect. Now take it further. Put a positive mass and a negative mass side by side. The positive mass pulls the negative mass with gravity, but the negative mass repels the positive one. That should cancel out, but it doesn't. Instead, the two masses chase each other forever, accelerating without limit, without input. Energy comes from nowhere. That's the paradox. This violates what we call conservation of momentum and conservation of energy, two of the most sacred laws in all of physics. And yet mathematically, it's allowed. In fact, some equations not only permit negative mass, they don't forbid it. General relativity allows solutions where negative mass exists, so why don't we see it? One possibility: it might be unstable. If a negative mass particle ever formed, it would instantly shoot off into infinity, or tear itself apart in bizarre interactions. Another possibility: it exists only in symmetrical pairs with positive mass, perfectly cancelling each other out. The universe could be filled with negative mass, but we wouldn't notice because its effects are cloaked. And then there's the wildest idea. Maybe dark energy is negative mass. The universe is expanding, and that expansion is accelerating. Something is pushing galaxies apart. We call that something dark energy, but we don't know what it is. Some physicists believe negative mass could explain it. An invisible, repulsive substance woven through the cosmos, inflating space, not with a bang, but with a gentle, continuous push. There have even been experimental suggestions, ultra-cold atoms behaving in ways that mimic negative mass. In 2017, researchers created a Bose-Einstein condensate with properties that acted like it had negative mass. When they applied force, the atoms moved opposite the direction of push. It wasn't pure negative mass, but it pointed toward the possibility that nature can simulate it under extreme conditions. And here's the philosophical sting. If negative mass exists, then our entire model of motion, resistance, and force becomes relative. The universe may contain not one kind of reality, but two, mirrored and incompatible, coexisting invisibly. A kind of anti-reality that behaves in reverse, forever evading detection, yet constantly shaping the cosmos from beneath. So next time you drop something and watch it fall, consider, somewhere, maybe in a distant fold of space-time, there's a mirror object rising when yours falls, repelling when you attract, accelerating into mystery when you pause. The negative mass paradox asks not whether such matter is real, but whether we've misunderstood what real means. It's not about proving that something impossible exists. It's about accepting that physics may be stranger than we are built to perceive. Where is the center of the universe? It's a question that seems simple, maybe even childlike. Surely the Big Bang must have exploded from a central point, and everything else expanded outward from there. So shouldn't there be a middle? Core? A cosmic origin you could point to on some unimaginable map. But here's the twist. There isn't one. This is the paradox of the uncertain center. The strange, unsettling idea that the universe has no fixed middle, no privileged point of expansion, and that wherever you are, you're already at the center. To understand this, imagine a balloon. Now draw tiny dots all over it. These dots represent galaxies. As the balloon inflates, each dot moves away from the others. The surface stretches, the space between the dots grows, but none of the dots is the center of the expansion. The center of the balloon exists outside the surface itself, in another dimension. From the perspective of a two-dimensional being living on that surface, there's no identifiable center. Every point sees every other point moving away. Our universe works the same way, but in 3 dimensions. The Big Bang wasn't an explosion in space, it was an expansion of space. Space itself stretches, carrying galaxies with it. No matter where you are, you observe everything else moving away, and the further away something is, the faster it recedes. This isn't because you're special, it's because every point experiences the same thing. You are at the center, but so is everyone else. This leads to the paradox. If everyone is at the center, then no one is. The idea of a central point becomes meaningless. In a universe governed by general relativity, location is relative. Perspective defines experience. The geometry of space-time doesn't allow for a single origin point within its observable surface. The center is smeared across all of space, and yet we keep looking for one. Our minds crave anchoring points. We want to know where we are in relation to everything else, but in cosmology, there is no cosmic GPS. The universe doesn't provide fixed coordinates. Even our own Milky Way galaxy is drifting, carried along by gravitational tides, spiraling through cosmic filaments with no ultimate destination. Movement, expansion, gravity, none of them require a center to operate, and it gets weirder. Quantum mechanics introduces its own version of the uncertain center. In quantum field theory, particles don't have defined positions until measured. They exist as probability clouds, blurred across space. There is no definite there until you look. The center of an electron? Undefined. The center of a wave function? A shifting statistical guess. The universe itself, in its earliest quantum state, may not have had a precise location at all, just a smeared, uncertain presence that became real only through expansion. This echoes in observer-based physics. In many interpretations of quantum mechanics, measurement creates outcomes. Without an observer, the system floats in a cloud of possibilities. Without a reference point, center has no meaning. The act of asking where you are determines what where even means. So here's the philosophical sting. You might spend your life searching for the center of things, your purpose, your position, your meaning, only to discover that you've always been there, that everyone has, that the center is not a place, but a perspective, not a destination, but a decision. The uncertain center isn't just about cosmology. It's about how we orient ourselves in a universe with no edges, no anchors, and no cosmic throne. It's a reminder that meaning might not come from finding the middle, but from realizing that the middle follows you. So tonight, as you drift in thought, remember, the stars aren't fleeing from one point. They're all receding from you. And if you were on a distant planet, they do the same. You are the center of the universe, not uniquely, but necessarily. Gravity is the most familiar force in the universe, and yet it's the strangest. It holds galaxies together, tugs at every atom in your body, and makes dropped objects fall to the floor. But unlike other forces, gravity has no obvious carrier, no shield, no way to block it. It acts invisibly, instantly, and without resistance. And stranger still, it's felt even in the absence of weight. This is the paradox of the weightless pull, a force that drags everything toward everything else, yet seems to operate without effort, without friction, and even without mass. Let's begin with a classic contradiction. Astronauts orbiting Earth appear weightless, yet they are under the constant pull of gravity. They float not because gravity is gone, but because they are in a state of continuous free fall, moving forward fast enough that they perpetually fall around the planet rather than into it. Their mass hasn't changed. Gravity hasn't switched off. But the sensation of weight, the pressure between body and floor, is gone. They are falling, and never hitting bottom. This reveals something fundamental. Weight is not gravity. Weight is the experience of resisting gravity, of standing still against it. When that resistance vanishes, so does the sensation of weight. But the pull remains, a force you can't feel, yet one that never stops acting. Now enter Einstein's view. In general relativity, gravity isn't a force at all. It's a curvature of space-time. Objects move along the straightest paths in a curved geometry. When the ground resists your fall, you feel weight. But when there's no resistance, like in orbit, you move freely along the curve and the sensation disappears. So gravity is pulling you, even when you feel nothing. That's the first layer of the paradox. Now let's get stranger. In Newtonian physics, gravity is a mutual attraction between masses. But gravity is also felt by massless particles, like light. Photons have no rest mass, yet they bend around stars and vanish into black holes. How can something without mass be pulled? Because gravity doesn't care about weight. It shapes the very path of reality. Light moves in straight lines. But when space-time itself curves, those straight lines curve with it. The pull isn't into space, it's a deformation of space. No mass required. And it gets weirder still. Black holes, the most intense gravitational objects in the universe, emit no light, no particles, no radiation, except Hawking radiation, theoretically. Yet, they exert tremendous pull. Stand next to one, if you could, and you'd feel nothing at the event horizon. No bump, no shock. Cross the threshold and gravity doesn't increase. It simply becomes inescapable. The pull feels weightless, yet absolute. This is the core of the paradox. Gravity operates like an invisible hand that never touches anything. It causes motion without contact, collapse without compression, acceleration without effort. Unlike electromagnetism, gravity cannot be shielded. There is no gravitational insulator. You can't build a box to block it. It acts at all scales, across all distances, and through all matter. It has infinite reach, yet acts on the smallest particles. Some physicists believe gravity may not even be fundamental. It might be emergent, a result of quantum entanglement or entropy, rising from the collective behavior of information rather than particles. If that's true, then gravity isn't a force at all, but an illusion created by deeper laws we don't yet understand. So when you feel the tug of gravity, you're not feeling something doing the pulling. You're feeling space itself guiding your path. And when you don't feel it, when you're floating, drifting, dreaming, it's still there, curving the world beneath you in silence. The weightless pull is the paradox of presence without pressure, of action without sensation, of a universe held together by something you never truly feel yet never escape. Draw a line on a piece of paper. Simple, right? A straight path from one point to another. But now imagine zooming in, closer, closer still. You reach the grain of the paper, then the molecules of the ink, then the vibrating atoms, and beyond them, nothing solid, just quantum probabilities. Eventually you realize something unsettling. The line you drew, so clear to your eye, has no fundamental existence at all. It's a concept, not a structure. A boundary that dissolves the moment you look too closely. This is the paradox of the collapsing line. The idea that anything continuous becomes fragmented, uncertain, or meaningless when examined at the smallest scales. That what appears smooth and real is built from cracks and voids. In classical mathematics, a line is infinitely divisible. Between any 2 points, no matter how close, there's always another point, a pure continuum. This is the foundation of calculus and geometry. Space, time, and motion all depend on this seamless continuity. But nature doesn't seem to agree. At the quantum level, the smoothness breaks. Quantum mechanics introduces a fundamental limit to precision. Heisenberg's uncertainty principle. You can't know both the position and momentum of a particle exactly. Try to draw a line of where a particle has been, and it fuzzes out. The more precisely you trace its path, the less real that path becomes. What we see as a clean trajectory is actually a blur of probabilities. The line collapses under scrutiny. And this isn't just about particles. Even space-time itself might not be smooth. Some theories of quantum gravity, like loop quantum gravity, propose that space and time come in discrete chunks, tiny, indivisible units at the Planck scale. Below this scale, the very concept of a line or a curve stops making sense. You can't draw a smooth circle on graph paper if the squares are too big. Likewise, you can't trace a path through space-time if space-time is pixelated. Now consider this. Light travels in straight lines, right? But in curved space-time, straight lines become geodesics, the shortest path between 2 points in a warped geometry. And if space-time is bending, shifting, or fluctuating at the quantum level, those straight lines are constantly collapsing and reforming. The very act of defining a line becomes an act of approximation. This paradox haunts measurement too. In geometry, we can define a line of length 1.5 centimeters with infinite precision. But in the physical world, that line is meaningless unless you specify how you're measuring it and with what tool. At quantum scales, your measuring device influences the system. You're no longer seeing the line, you're disturbing it. Reality collapses into interaction. And here's the deeper twist. This paradox doesn't just live in physics, it infects thought itself. Conceptual lines, the boundaries we draw between ideas, categories, and identities, also collapse when examined too closely. Good and evil, truth and falsehood, self and other. These seem like clear lines, but they blur at the edges. What appears distinct from a distance dissolves into ambiguity up close. Our logic, our language, our morality, all are built on collapsing lines. So what does this mean for you? It means that the world you see as stable, continuous, and navigable is stitched together by approximations. That every path you follow is really a cloud of uncertainty, held together by the illusion of definition. That the boundaries you trust might not exist at all when you dig deep enough. The collapsing line reminds us that reality is only smooth because we zoom out. At the deepest level, everything breaks, not in chaos, but in uncertainty. The more we demand precision, the more it dissolves. So tonight, as your thoughts drift, consider every line you've ever drawn, on paper, in space, in your mind. How many of them would hold if you looked too close? Where does the universe end? It's a question as old as wonder itself. If space is expanding, what is it expanding into? If the cosmos has a shape, what lies beyond its edges? And if it has no edges, no boundaries at all, how can something infinite still be expanding? This is the paradox of the boundless edge, the mystery of a universe that is finite in structure, infinite in presence, and forever escaping the grip of definition. Let's start with the familiar. Picture a balloon being inflated. Imagine tiny dots on its surface, galaxies in a stretching cosmos. As the balloon grows, the dots move away from each other, not because they're moving through space, but because the space between them is expanding. Now here's the twist. The surface of the balloon has no edge. You can travel around it forever without falling off. And yet, it's a finite surface, finite area, but no boundary. This is how many cosmologists describe our universe: a finite, unbounded structure, a three-dimensional analog of the balloon's surface. No edge, no wall. just space folding back on itself in ways we can't directly observe. But if there's no edge, then what are we expanding into? The answer, as strange as it sounds, maybe nothing. Not empty space, not another dimension, just more of the universe. Space isn't expanding into a pre-existing arena. It's creating new room as it goes. The universe isn't moving through space. It is space. And that means there is no outside, no external container, just the inside, blooming. So the paradox sharpens. The universe has no edge, but it's still growing. It has no boundary, yet we can talk about how big it is. It has no outside, yet we talk about expansion. We use words that imply limits to describe something that may have none, and it gets even more disorienting. If the universe is infinite, as some models suggest, then it's always been infinite. It didn't start from a point and stretch into infinity. It was infinite at the start. The expansion we observe, the redshifts, the cooling of background radiation, the increasing distances, is not the stretching of space into new territory. It's the deepening of structure within infinite territory. If that's hard to picture, you're not alone. Human cognition is built on edges, borders, frames, boundaries. Every experience you've ever had ends somewhere. Every room has walls. Every object has sides. But the universe might not. And that leaves us with a concept we struggle to hold. A boundless edge. Something that encloses everything while enclosing nothing. Some theorists suggest space may be topologically closed, like the 3D version of a sphere or torus. Travel far enough in one direction, and you'd return to your starting point, not because space ends, but because it curves. There's no outside the curve, just more curve, more path, more presence. Others propose multiverse models, where our universe is just one bubble in a foam of infinite others, each with its own laws, its own physics. In that view, the universe might have an edge of sorts, but only when seen from a higher dimensional vantage point. An edge that is not an edge from our perspective, but a gateway from another. And here's where the paradox turns inward. If the universe has no edge, then neither does your position in it. You are not near the center. You are not near the edge. You are exactly where everything else is, in the middle of a boundless experience, held by no frame, limited by no wall. The boundless edge is the final whisper of a universe that refuses definition, a reality that expands without escaping, that contains all things while touching nothing outside itself, because there is no outside. So as you drift towards sleep, try to imagine a place that has no border, a path that never ends, because there was never a boundary to begin with. You've journeyed through a universe that bends, breaks, and rewrites itself with every step. You've fallen upward, floated in a wired vacuum, stood at the edge of infinity, and questioned whether motion, time, and even gravity are as real as they seem. And maybe now, as you lie in the dark, breathing slowly, mind adrift, you feel something deeper than confusion. You feel small, but not insignificant. You feel like a question still unfolding. That's what paradoxes do. They don't close doors. They leave them open, barely ajar, just enough to let in the wind. They remind you that knowledge isn't always about having answers, but about learning how to live with unresolvable wonder. Every scientific truth you were taught may one day be turned inside out by a deeper insight. And every law of nature may be nothing more than a temporary agreement between what we see and what we don't yet understand. The greatest minds in history have stood on these same edges, staring into the dark, listening for the universe to whisper something new. Some came back with equations, some with silence. All of them, eventually, with awe. And now, maybe you carry a piece of that too. So rest now. Let the uncertainty wrap around you like a soft blanket. Let your mind wander through bending light, collapsing lines, and echoing time. The paradoxes will still be here tomorrow, waiting to unravel everything you thought you knew. Because reality isn't fixed. It's falling, it's looping, it's dreaming, and so are you.